हेलो अस्सलाम वालेकुम।
Hey, Assalamualaikum.
हम
How's it
दोनों
going?
पहले तैयारी करें कनेक्टिंग फ्रेगमेंट्स।
Can you hear me?
अब हमें हमारे बच्चों के बारे में कुछ तय करनी चाहिए। हाँ।
I think there's some background
Sorry, I
noise.
think there's some. Let me check. There's some other audio playing on. Okay, so Shajit, can you hear me?
Yeah, I can hear you fine. What about you?
Yeah, it's very clear. Thank you. So, uh, as yesterday you were earlier than the time, and it's a
Yeah,
good
I just
habit.
wanted to, I want to make sure that everything is set up. So I actually wanted to ask you, so is this a workshop that you're organizing? Is it based on your institution or is it open to everyone? Or like how does it work?
Yeah, like it was open to like everyone, and but I guess most of the participants are from the Islamabad and Rawalpindi region, the capital,
Okay.
because I'm based here. So plus there's this fact that so it's an effort to promote string theory in Pakistan, and like many students, as you know, like they are excited about it, but since the mathematics is so difficult that they never get to
Mm.
really know what string theory is. And I'm extremely grateful that your yesterday's lecture, it took long, but without that it's impossible to communicate what string theory is. And I wish that students did, the participants worked out things. So yes, so I basically just set up an institute, just to organize things according to my will. But yes, it was open to the university students, and since it's summers, so they have time and they can attend.
Mhm. I see. It's about time, but should we wait a few more minutes before some other?
Yeah, but okay, uh, because the lectures are being recorded, and I know that there are many participants who prefer to watch the recording. So
Oh, okay. I see.
yeah, maybe we
Uh,
can wait one more minute and then we can just.
okay.
So yeah,
Oh,
meanwhile,
so today, sorry, today you have the afternoon, yeah, the afternoon session. So it's I think mine is already afternoon session, but in the second session, so what's the gap? So I mean, I was just trying to figure out. I don't have the luxury to go over time today, right?
yes, I was thinking about this, that today I think it would be advisable to finish at the sharp time so that
Mhm.
there's at least
Okay.
half an hour break, and then
Okay. Fair
so
enough.
I
So
think in that
yeah.
respect, we should also start right now. You can share your
Mhm.
screen because we would like to end at the sharp
Mhm.
end time.
Got it. Okay. So let's connect my iPad. Um, is it- what's going on? Oh. Mhm. So I tried to share it, but somehow. Oh.
It's replying there also.
So let
Okay,
me
so
restart.
you're
Just,
unable to
just
share
let
the
me
screen?
Yeah, it's not letting me. So let me restart my computer. Just once. Give me 1 second.
Okay, okay. It's okay.
Mm.
So I noticed that you don't use good notes or such fancy things. Okay. हाँ कचरा बस फेंक देना.
Sorry about that. Let me try now.
It's okay. So now the screen might get shared.
Yeah. Hmm. What's going on here? Problem here. Not sure.
Are all the devices on the same Wi-Fi? This might be affecting like your writing iPad and
Yes, they are. Because I'm in my office. Hmm. Sorry about this.
so maybe turn off the Wi-Fi on the device and turn on again. It's some glitch.
Yeah, something simple problem.
Well, we should have apprehended it that from yesterday also when the Notes app, lost all your part of your lecture.
Yeah, that's true. Um, Sorry, let's see.
Maybe try restarting your writing tablet.
Yeah, so,
Try restarting your writing device.
yeah,
Maybe you should try restarting the writing device.
I'm trying. Okay, I think now it's really working. Uh,
Maybe there are two options, like which screen you want to share, and you aren't picking the right option.
Yeah, maybe
That
that.
that it does sometime.
Okay, I think it's coming. Okay, sorry about that.
Yeah, finally.
Yeah, I don't know what's the problem, but anyway, so you can see my screen now, right?
Yes, we can see it.
And let's clean up a bit. Okay, so I don't know what this thing coming from, but ignore that. Okay, so I think I just want to quickly start um, to do with the one of the questions that was asked last time. I think I did not answer that quite correctly last time. So I think the question was about the generalization of strings, right? I forgot who asked that. Now, in string theory, we can actually have objects which you call the D-branes, and they arise when you talk about open strings, and they are sort of the complementary objects where that provides the endpoints for the open strings. Now, these D-branes can be dynamical and higher dimensional extended objects in string theory. So it sort of generalizes the concept of 1D string to some p-dimensional object. Now, having said that, it is more precise to understand them as a surface that defines the appropriate boundary conditions for the open strings. And also the tension charge, and they also have some sort of non-perturbative nature, which sort of set them apart from the traditional basic strings. So, okay, so let's move. Let's get back to our topic today. So this is I already listed the things that we're going to do today. So we'll talk about quantization, and the particular quantization is the Lightcon quantization. We'll talk about these residual symmetries. In the process, we'll talk about Lightcon gauge. Then we'll have solutions for the Lightcon coordinates, and then we lay out the quantization procedure. So let's move on. So we have seen that the Walsh-Heap description of the string theory is basically some sort of 2D field theory with some gauge symmetry, which comes from this reparametrization and Weil symmetry. Another name for the reparametrization symmetry is the diffeomorphism symmetry, right? Because ultimately it's some sort of active coordinate transformation in the Walsh-Heap for the Walsh-Heap coordinates. Now, so it's today we want to quantize this theory, and we're going to use what we call the Lightcon quantization. The idea is, what is it doing now? Something is very wrong. It's a Morpheus law, right? Everything that can go wrong will go wrong. No, the pen is not working. Let me try a different page.
Or maybe the pen is not charged, or the
No, it's
battery.
charged.
Oh, okay, it's 90%. Okay.
Something is very wrong today. Everything is going wrong. What's going on? Sorry about that. It's not letting me write. So whenever I'm touching it, it's doing this. Anyone have any solution?
Actually, earlier, that's what I was thinking to say. If you use a different app, like though it would take some time, maybe you should try first downloading GoodNotes. That is a better app. If you already have that, I think that's better than Notes.
GoodNotes. Let's see if I have it. I don't have GoodNotes, but is there anything else or I can write?
Yeah, try writing on Keynote so that we get an idea like where the problem is like.
But this is
No,
okay.
like start a new document. If there's a new option, start a new document and no, use that back arrow to go back and now click the plus to create a presentation, and then on that presentation, yeah, you can choose any theme or any.
Okay.
Yeah, just use the minimalist or basic white, and because that way we'll get to know that is it the
Oh, it's the pen somehow.
is it the app or the pen the problem?
I think the pen is giving me trouble, but here it's working a little.
Yeah, here it seems better. So
Yeah,
maybe if,
better. Um, just gonna try one more time. No, and this is a bit better now, right? So let's see. Nope. No, I think the Keynote was better. I need a blank page. How do I get a blank page?
uh, there's a plus icon at the bottom of
This
yeah.
maybe? Okay, I think this is okay. So so and then I keep plus adding slides, right? Or the plus.
Yes.
Okay. So so what is the sorry, we lost 15 minutes.
No, no, it's
That's no change. Yeah. So so we're gonna talk about light what the hell is this?
should we try like you do less math and maybe type?
Yeah, that's gonna be I can do that, but that's not gonna be fun,
Yeah,
right?
maybe go back to notes and just type and do less math.
Okay,
Okay, I think
this
that was the title box, so maybe it was. So just
okay.
write on, not on the title or the subtitle, but on the blank
Mhm.
page,
Okay,
maybe.
so okay, so let's see how it goes. So basically, the idea is for the light conjugate, it's a two-step process. So the first step is we will solve the constraints to figure out the physical classical solutions. Once we figure out the physical classical solutions, then we're going to quantize the physical solutions. And in the process, we'll keep track of the space-time Lorentz symmetry. So we'll see the details in a second. So before going into the details of this quantization, I want to start with something called the residual symmetry. So there's this notion of residual symmetry. So what does that mean? So idea is the following. So so we have seen that we have this Walsh-Diffeo, which is the reparametrization symmetry, and on top of that we have Weil symmetry, right? That's the local symmetries that you have seen last time, the gauge symmetry you've seen last time. Now, and we have seen that what it does when we use this symmetry to basically fix the gauge, right? So we basically can write down the metric. We can make it a flat metric, right? Walsh metric as a flat metric by making use of this gauge choices that brings this symmetries bring. So Now, what the residual symmetry means, so for example, if once we fix the gauge to this flat metric, then if we do further diffeomorphism and Weil transformation, then of course the metric is not going to be unit metric anymore, right? Because we're changing the coordinates and doing further Weil transformation. However, we can have a situation where the transformation done by the diffeomorphism can be undone by the Weil transformation, right? So one of them, the Weil transformation, can sort of observe the transformation of the change done by the diffeomorphism. So, and that's what we call the residual symmetry. So it's not a residual symmetry in the sense that it was not covered by diffeo or Weil. It's residual in the sense that it remains even after fixing the gauge. Now, how do we think about this? So, for example, I need to write. Okay, how do I get a blank page again? Do you know a new blank page?
Actually, someone has suggested that we should try Zoom whiteboard. Would you
Oh, really?
suggest that I create a Zoom whiteboard and
how do I write there? This part.
so let me just take a moment to do that. So,
but can I keep talking while you're doing that?
okay, because I think, okay, you try bringing a new page here because I think Zoom whiteboard will take us somewhere else.
Yeah. So how do I get a new page?
Yeah, with the same plus icon at the bottom. Blank.
Oh, okay. This is better. Okay, good. I like this. Okay. Now, so what? Oh, okay. I was happy too early. So what do I have is this, right? Something like that. We fix the gauge. Now, as I said, we're going to look at the residual symmetry. So what it means is we're going to do diffeo and Weil in such a way that the Weil and diffeo sort of cancel each other, and we have a symmetry. So I write down this in the following way. So I have n prime alpha beta, which is for the sigma prime. So I'm doing some diffeo here, and then I'm going to match it with the Weil transformation, which is this, something like this, right? Something like this. Now, notice that the left-hand side, I can write it as, say, something like, and this is very annoying, something like this, right? And then I have to do the diffeomorphism. So I had these coordinates, the sigma, alpha, let's say, and then the new, let's put them right, sigma beta, right? So I just write down the transformation, right? I'm writing down the diffeo, the new the new metric in terms of the old, and then on the right hand side I have this eta alpha beta. Now, if we demand this, if we do a transformation, if we do an infinitesimal, so we're doing infinitesimal diffeomorphism, infinitesimal reparametrization. So let's write down these guys as some identity plus some variation. Now we're going to choose the variation, some sort of expansion. So you're going to do it like this, right? And since you're demanding infinitesimal transformation, the next term is going to be higher order in epsilon, so you're going to drop that. So you're going to just leave it like this. So this is our coordinates transformation. And the same thing I do for the other term. So I get a delta nu beta plus this beta epsilon nu, right? Something like that. So, for the other term. So when I combine these three and write it neatly, what I get is the first term, the delta, all the deltas gives me the eta, brings back the flat metric, plus then I'll get something like epsilon beta plus epsilon alpha, something like this. And then, of course, the higher order terms, which we can sort of ignore. And then on the right-hand side, we'll have the wild part, right? This is so. So you see the upshot here is now with this we're matching, right, the wild transformation and the infinite diffeomorphism. Now with this I can now combine this into one single relation. So something like alpha epsilon beta plus del beta epsilon alpha equals, oh, it's very annoying, del alpha epsilon beta plus del beta epsilon alpha equals this eta alpha beta, right? Something like this. Where, of course, this guy is, something like after simplification. So, so the point is that the diffeo plus the wild transformation satisfying this condition is still a symmetry, right? So that's the residual symmetry we have. Okay, good. Now, so what do we go from there? So now, from the this residual symmetry, it is possible, since we have a residual symmetry, it's possible to make additional gauge choices, right? This symmetry gives us a, of course, it has to satisfy that condition that we just wrote. Now, the best way to implement this would be going to the light cone gauge. But before that, so as I said, there's a residual symmetry, and and to implement that residual symmetry, you can fix a gauge, and that gauge is what we call the light cone gauge. Now, before going there, what I'm going to first introduce is called the light cone space-time coordinates. So you have seen previously that we wrote down things in terms of the light cone wall sheet coordinates, right? Now we're going to introduce also light cone space-time coordinates. So what that means is we're going to write down these space-time coordinates in this way: x naught plus minus x d minus 1, something like that, right? So you're going to isolate the space direction and the time direction and construct two new coordinates, the same way we did it for the wall sheet. So in this language, we basically have, so our coordinates are now sort of this x plus minus, and then this xi, right? So they're altogether, it's again a d-dimensional spacetime. Now, I think in the Baker textbook, they put an additional factor, which we're going to ignore. I'll be following the Tong the convention followed in David Tong's lectures, which is just that. Now, so here you see that when I'm going to the light cone coordinates, it's no longer manifestly Lorentz invariant anymore. So we're sort of picking out a particular directions, right? Particular space direction, like maybe x1 or something for this. So, but you might say, okay, it's okay. I mean, since we started with the Lorentz invariant theory, so at the end of the day, we might, it will be preserved. But this is actually, unfortunately, not always true. So what happens is sometimes the classical symmetries, they don't survive the quantization process, and what you call the anomaly. Now, so we'll see later that under certain condition, the Lorentz invariant can be preserved in this case. Now, here also when I invoke this light cone coordinates for the space-time coordinates, then of course, as you have seen last time, that we basically get an off-diagonal kind of metric, right? For that piece. So the inner product is defined slightly differently, which means, for example, if I want to raise or lower indices, because now the metric is off diagonal, or at least that part of the metric is off diagonal. So what you get is, for example, if I have a vector minus, if I want to lower this, is going to be related basically by this, because the cross terms are basically surviving. In a similar way, for plus, if we want to lower it, we're going to get a minus. But the I components can be, because that's still the usual Minkowski, usual flat metric. So it's diagonal metric, so we get the same thing. Now the question is, so the question is now what simplification can we get by using this residual symmetry, right? So we have the residual symmetry, and what kind of simplification we can get out of this. So so let's talk about that. Now, so notice that we derived in the first part of the lecture that we have this kind of condition. It's very annoying. So we have, okay, now what happened? Okay, so we have this kind of condition, right? Oh. Okay. So we have this condition that alpha epsilon beta plus beta epsilon alpha is lambda eta alpha beta, right? We have this kind of condition for the residual symmetry that we need to satisfy. Now, interestingly, this condition, I'll show you at least. Well, this iPad is acting weird, but I'll try as the best I can. So this transformation is essentially corresponds to a transformation at the level of the space-time coordinates, something like this. Something like this. And then for sigma, sorry, it's minus. So I'll try to justify that in a second. But the point is this kind of transformation that basically implies at the level of the parameterization for the Walsh-Head coordinates, this kind of parameterization. And you can see if you look at this expression closely, it's sort of you can immediately see that this implies that this tau and tau twiddle and sigma twiddle actually satisfy the wave equations, right? Which is quite useful because our original string coordinates also satisfy some sort of wave equation, right? With some constant. So that's an interesting point. Now the question is, how do I see that this condition and this parameterization, this reparameterization are actually consistent with each other? So let's try to see that. Now, to see that, what I can do is I can write down this, let's say alpha beta, this new metric, the Twiddle metric. I think I switched to H here for the Walsh-Head metric, but it's the same thing. I think when I was writing my notes, I was looking at different resources and it happened. So the coordinate transformation I can do is something like this, and then same term, nu, and then the sigma beta, and then H mu nu, right? Something like that. Now notice that this is the generic coordinate transformation. Now here if we so for example mu here is 0, 1, so tau sigma in my notation. So here I'm already using mu nu, but it's basically the Walsh-Head coordinates. Now what I mean is, so if I compute, let's say H00 term, then what I get is d sigma tau mu d tau, and then d sigma nu d tau H mu nu, right? Something like that. And similarly, I can write down other terms. Now, if I expand this, now I get d twiddle d sigma, and then d twiddle d tau H00, and I have another terms which is d twiddle d tau d twiddle d tau h11, right? Something like that. Now, so what I'm doing here again, just to remind you, in the previous slide, remember that I wrote down the reparameterization as a which satisfies some sort of wave equation, right? So I'm justifying that. So our Toodle, our Toodle here is basically some function of tau plus sigma and some function of tau minus sigma. And similarly, the sigma Toodle will be something like, again, similar, right? Tau plus sigma and then tau minus sigma, something like that, right? That's what we use, what I showed in the previous slide. Now, if I plug this, here in this expression, what I get is something like the following. So you have to do, plugging this, and you have to do 2 lines of algebra. Because of time constant, we already lost quite a bit of time. I'm just going to show you the final expression. You get something like this. Now, in a similar way, I can compute this h, the cross term, right, the orthogonal term, which is going to be something like the Toodle, the tau, d sigma Toodle, this sigma h mu nu, and then we have to expand it, right? So we're going to have d tau Toodle, d tau Toodle, d sigma h00, d tau Toodle, d tau, d sigma Toodle, d sigma h01, and last would be, there's actually one more, d tau Toodle, d sigma h10, and finally there is d Toodle, d tau, and d tau Toodle, d sigma h11. So lots of different terms, but the upshot is altogether when I compute this, when I compute all these derivatives, I'm going to end up with something like, so again, I'm skipping a couple of lines here. You have to plug all of this, all of these derivatives, and then you do a simplification. And what you're going to get is something like f dot g prime minus g dot f prime, something like that. Now, notice that for our case, we can actually consider, we can actually set the derivative, the time derivative and the space derivative sort of identical. The idea is very simple. So if we consider some function, just to give a sense, if we consider some function of sigma plus tau, let's say as an example, a sigma plus tau square. So you can see if I do f dot and if I do f prime, it's basically the same thing from the perspective of the derivative. Right? I get the same expression. So what that means is basically this can be set to 0. So and so in a similar way, you can compute the h11 term, and you'll see you'll get a factor like this. So the upshot is when you do this particular transformation, which satisfies the wave equation, it actually is consistent with an overall phase factor in your metric, right? So that can be absorbed by the Weyl transformation. So that's why this is the right residual transformation. I hope that this clarifies the point. Okay. Okay. So let me move on. So okay. So now what we have? So we see that we have some residual gauge symmetry, and we sort of know how to think about how to consider what kind of parameterization give rise to that. Now let's get back to the actual business, right? So we have our equation of motion, which is our equation of motion is like like this, right? Something like this, as you've seen last time. And also we have some constant equation, which is plus xl square equals minus xr square, something like that, right? And remember that this x mu was we had this left mover and the right mover, right? And then the right mover, which was XL, which was sigma, something like this. Now, what you're going to do, we have also introduced this light coordinates for the space-time, right? So we also have now x plus minus equals this x naught. Let's pick one of the space directions, something like this. Maybe we can just pick maybe just x1, for example, for this. So, something like x naught plus x1. So then with these ingredients, we can basically write down the x plus as, if I combine this, we can write down this, the left mover plus, and then xr minus, sorry, plus sigma minus, something like that. Now, so we want to now we want to fix a gauge, right? We have a residual reparameterization symmetry. We want to fix a gauge, and as I mentioned, the gauge we're going to consider is the light cone gauge. So we need to write down this and this, right? These guys. So what I'm going to write down, what I'm going to pick for this left is 1/2 x plus 1/2 alpha prime p plus sigma plus. And for the right, I'm going to pick, I'm going to choose x plus 1/2 alpha prime p plus sigma minus. I'll give the motivation in a second, right? I'm not just making this thing up, right? I'll get there, but for now, just stick with me. So then the total x plus is going to look like x plus. So that's, you can see that I picked these numbers carefully so that we have the right expression, alpha p plus tau, something like that. And because this combines gives you tau. So and this is what you call the light cone gauge, right? This is the light cone gauge choice. And in principle, we can observe the x plus by some sort of shifting, by doing a shift on tau coordinates. Okay, now let me give you a motivation, right? How do I get there? So for the motivation, okay. So I'm just trying to, I'm going to sketch the justification for this, right? X plus equals, this part of the iPad is somehow broken, I think. Now I actually start to suspect that it's happened during my flight coming back from this. I think maybe the screen is broken or something. That's why all these writings are not working. So, so we have this, I'm just giving a justification for this. I'm using a tootle because I'm going to use some parameterization for this. So notice that, so why this kind of structure? Why this kind of gauge you are considering? What is the motivation? So remember that we've seen that the reparameterization that we were allowed from the residual symmetry, the reparameterization we're allowed to do from the residual symmetry is something like this, right? F tau plus sigma and then G tau minus sigma. So this kind of transformation, right? This kind of parameterization. Now, notice that our x mu, right, this space-time coordinates, tau sigma, is basically this, right? This x left movers and right movers, something like that. And here in this language, because we went to the light cone coordinates, and then light cone coordinates is basically plus, minus, and I, right? These are the space-time index, right? We have this x naught plus x1 and x naught minus x1, there's two coordinates, and then the rest is the transverse coordinates, we call it, right? The I coordinates, xi, big xi. So you see what I can write now, the x plus sort of as XL plus and then XR plus, something like that, right? With the appropriate, with the appropriate code independence. Now, so you see, there is a similarity between the form. So what I mean is, if we choose if I choose F to be, let's say, some BL XL X mu L plus CL, and then G to be BR XR mu plus CR, I can choose that, right? Because this F is related to that, which is a function of tau plus sigma, which is consistent with the statement. So it's a consistent choice, right, for F and G. From there, you can immediately see that from their functional dependence. So what that means is, if I make this consistent choice, as you can see, their functional dependence is clearly matched. So I can write down this tau twiddle as, let's say, BL X. So I skipped one line here. So then we can choose a particular coordinate, right? We can choose a particular coordinate to fix that. Whereas, for example, I can choose this X plus. So if I choose a particular mu, say the plus one, right? So I choose this mu plus one, and then I can write down the twiddle as plus L plus CL, right? That's the F. And then I can write down the second part, the B part, sorry, the G part as B sub R, this CR, right? With this choice. And these are these A, B's are basically free parameters. We can choose them as we wish. Now, notice that I can simplify this expression. So I can write like BL XL plus BR XR plus, and then CL plus CR. Now, if I choose BL and BR to be equal to, let's say, 1 plus alpha prime P plus, something like that. And then these guys to be minus X plus to alpha prime P prime, sorry, P plus, then you can immediately see what I get is this. I plug it back. So this tells you the gauge choice that I made is consistent with the residual symmetry, right? And and the associated reparametrization. I hope that clarifies the motivation. Okay, now where do I go from here? So we fixed. So we have X plus, X minus, and X sub i's, right? These are the coordinates, space-time. So we fix a gauge. Sorry, the residual gauge symmetry. We use it to fix for X plus, right? Now we're going to find a solution for X minus. So remember, again, the motivation is what? We're trying to find the physical space, the physical solutions, right? And then once you get all the physical solutions, then we're going to quantize the system, right? So that's the goal. And of course, the idea is to deal with the constraints, right? The constraints are telling us which is physical, which is not. So now let's go to the, so we're now going to go for the solution of X minus, right? This part. So, and we have now we have the Lightcon gauge, right? X plus is equal to this small x plus plus alpha prime P plus and tau. Now, so let's first check the equation of motion for X minus. So what is the equation of motion for X minus? So it's like, we have seen it last time, right? Something like this. Now let's check, our standard answers, the usual answers. works or not. So our answer is something like this, right? Just a quick check. Something like this, right? So what I'm going to do, I'm going to plug it here, basically, roughly. So first, I compute this, which is going to be now just xr minus sigma minus. And then you can see that if I go to the full left-hand side of the wave of the equation of motion, then this becomes basically sigma minus. So this basically becomes 0. So it's satisfied the answer still works, right? The answer still satisfy the equation of motion. Now we have two constraint equations, right? These all constraint equations. And so what are the constraints? So we had this delta plus x square, and then we had delta minus x square equals 0, right? These were the constraints, right, that we had last time. Now what we're going to do is so you're going to see now the advantage of taking the light cone gauge. So what will happen is, because of the light cone gauge, we can actually completely determine this x minus. Because of the light cone gauge, we can completely find the x minus from these constraints. So that's the option. And what I mean is the following. So let's try to again, I'm gonna, because of the time constraint and the iPad being acting weird, I'm gonna just sketch the computation. So what you have is something like this, right? This is your constraint, okay? Something like this. Now notice that if I use this one, what I get is basically x mu, and then this is plus x mu equals 0. And then I can expand it as, you know, plus x plus, d partial plus minus x minus. I'm using that inner product thing that I mentioned earlier, right? That when you want to pull up or down, you have to be careful, because the plus becomes minus with the sign and so on, right? And then the plus x minus plus minus x plus, and then this is equal to plus xi d plus xi, right? I'm just expanding now this first line. So if I simplify this, it's gonna look something like this. X minus is equal to sum I equals 1 d minus 2 plus xi d plus xi, something like that. Okay, so so far I haven't used the light cone gauge, right? I just simplified the expression. Now I'm going to use the light cone gauge. So remember, our light cone gauge was what? X plus was equal to small x plus alpha prime p plus tau, right? Something like that. That was our light cone gauge. So I'm going to use it now in this expression. So for this expression, so if I start from here and I do d plus partial plus x plus, then you know, so I just take the derivative of that, and then again remember that this is basically sigma plus sigma minus, something like that, right? So if I do now do a derivative with respect to this partial plus, what I get is alpha prime p plus over 2, and I can plug it here on the constraint. So if I plug it here in the constraint, so I have a 2 here, I have a 2 here. So after simplification, what I get is dx xl minus, one more thing here. This second term, I can write it as, XL minus sigma plus, and then XR minus sigma minus, right? I can write down the X minus in this way. And then when I apply this, you can see that the second term is going to go 0, and we are only left with the first term. So after all this mumbo jumbo, what you essentially get is this constraint after simplification. So you should, you should make your hands dirty and try some of these computations at home. It's d minus 2, and then partial xi, partial xi. So this is something like this, right? So this is our new constraint. And of course, I can write down the other one, the right one, for in a similar, so it's a similar computation from the other constraint. So from this, if I start from here, then I get alpha prime p plus, and then sum I d minus 2 plus xi plus xi, something like that. So so these are our constant now, right? And so let's write down the mode expansion for the wave equation. So if we do the usual mode expansion for the wave equation, I'm going to get something like x minus sigma plus, then 1/2 x minus 1/2. You have seen it last times, right? So it's very similar ideas. I alpha prime over 2, and then n not equals 0, 1 over n alpha n toodle minus e to the power I n sigma plus. And for the right one, you go minus. So again, I'm solving for the x minus, right? So that's why this is the x minus part, the two left and the right movers of x minus coordinates, right? X minus plus 1/2 alpha prime minus sigma minus I alpha prime over, alpha prime over 2, and then, same thing, basically. And minus to the power I and sigma minus. So this is our mode expansion. Now again, this x minus is sort of is an undetermined integration constant, but from we have rewritten the constant equation after plugging the light cone gauge, right? The last expression in the previous page, the last two expressions in the previous page. So it turns out these quantities, this p minus alpha n minus alpha n minus toodle, they're all basically are fixed by those constraints, right? We'll see that in the next slide. Okay, so let's look into that. So if we look at the since it's very finicky, so I'm not going to try to go back. So if you look at your constant equations, the two new constant equations that we wrote, you'll see that from that constant equation we can actually look into the this mode, alpha n minus modes, right? So if you look at the left hand side of the constant equation and the right hand side of the constant equation, and write things in terms of the do your mode expansion, then you can write down alpha n minus equals 1 over 2 alpha prime 1 over p plus 1 over p plus what did I do? Summation m so infinity I want to d minus 2 alpha n minus m I alpha I, something like that. right? If I apply it in the constant equation. Now for the alpha naught, the zeroth mode, we can set. I mean, we have seen it last time, right? When we did the classical case, right? We set the zeroth mode with the momentum. So we're going to do the same thing here. For the zeroth mode, we have this p minus. So if we use this, then from here we get alpha prime over 2 p minus, p minus, then 2 alpha prime over 1. I'm just bringing this term on the right hand side, and then 1 over p plus, and then you get this, can rewrite it as this, 1/2. Again, I'm extracting the zeroth mode from here. The zeroth mode in the transverse direction. So going to be 1/2 alpha prime pi, and then you'll have the rest of the modes, right? So I extracted the zeroth mode, so I have alpha ni alpha minus ni. So maybe I'll just highlight how I get there. So two things, right? So first so I want to plug this, right? So the zeroth mode. So in this expression, I basically plug n equals 0, right? So plug n equals 0 in this expression on the right hand side. Now, after doing that, I actually relabeled m to n. So you can see that the n is back here because it's basically originally was m, right? I'm just relabeled it. That's it. And then you get this expression. So the upshot here is, after doing the simplification, I can write down in this form. So this is the important part. I can write it down in this form. I equals 1 d minus 2, 1/2 alpha prime pi, and then sum n not equals 0, alpha ni, alpha minus ni, something like that. And of course, I will have exactly the same equation for the Tootle part, right? So I'll also can derive another equation for the Tootle part. So 1 d minus 2 alpha prime pi, and then this is again alpha ni Tootle, alpha minus ni Tootle. So this is my two new constant equation, you can call. Now remember that last time when you were at this situation, we basically what we did, we sort of combined all the momentums and then identified that with the mass term, mass squared term, and then wrote down the mass term in terms of the oscillators, right? Oscillator modes. So we're going to exactly do the same. Again, the idea was to do the level matching. So we're going to still exactly do the same. So we're going to so you can see it's actually a very similar idea. So I have this p plus downstairs and I have a p minus upstairs here. So if I bring it to the left hand side, I'll get a p minus p plus, and then I also have the rest of the pi. So all together, it's actually the new inner product for p mu, right, in the light cone gauge. So this all together can be written as m square. And again, m square is going to be equal to this part, and similarly for the Tootle. So what I mean is, you're going to get something like this: m square equals, this 2p plus p minus I equals 1 to d minus 2 pi. So that's the full p mu in light cone gauge, and then equals to, for sorry, no, not light cone gauge, I mean in light cone coordinates, and then alpha prime equals I equals 1 d minus 2 n 0 alpha minus n alpha ni, something like this. And similarly for the Tootle case, right? Tootle. So so you get a very similar thing, but there is an interesting point here. So notice that this it goes from I to d minus 2. So the sum is only over the transverse oscillators, you can call it. That's the difference from what you had before. Now notice, just to a point of caution here, the string is not necessarily living on the some x0 x1 plane or x0 x d minus 1 plane or anything. So what we're doing here is this, once we specify these modes, once we specify these alpha I modes, these transverse modes, all the other oscillator modes can be determined from there. So in that sense, these are representing the sort of the physical excitations. Right? So these are the physical solutions that we're going to quantize later on. Okay, so what is the upshot so far? So we saw that the most general classical solution can be described by this d minus 2 times 2, right? There are two sets of transverse oscillators, right? And those are what? These alpha I, alpha I n and alpha I n twiddles, right? So they goes from 1 to d minus 2. So there's 2 times d minus 2 transverse oscillator modes. And of course, we also have some zero modes describing the center of mass and the momentum of the strings, right? So things like xi, pi for the transverse coordinates, and then p plus and x minus. Notice that x plus is not really can be actually absorbed, as I mentioned when you talked about the Lightcon gauge, can be actually absorbed by doing a shift on the tau, right? Because x, remember, x plus was big X plus was small x plus this 2 p prime, 2 p plus tau, right? So I can do a shift on tau and then can absorb the other one. And also the p minus is completely constrained by the constraint equations. Right? So these are the things that we're going to quantize. Oh, another point is here the p plus. So as I said, this can be absorbed by tau, right? So which means the conjugate quantity, this p plus is actually, so it's this is sort of the plus is in the Lightcon gauge, the plus is considered sort of the time-like direction, and minus is considered sort of the space-like direction. So in this sense, this is sort of time-like, and the reasoning is, you can see that it can be absorbed by tau. So the conjugate momenta for this is basically p minus, and the p minus is sort of the Lightcon energy or Lightcon Hamiltonian, you can think of when I promote it to an operator, right? So it's a sort of like going to be Lightcon Hamiltonian. So the commutation relation would be between these two. In a similar way, you can also realize that the conjugate of x plus, which is the space-like, x minus, which is the space-like, is going to be p plus, right? Which is the momentum. Okay, good. So we have all the basic ingredients. Now we are up to quantization. We have to go quickly. We have about 23 minutes. Okay. So what is quantization? So what is when I say we are going to quantize the theory, what do we mean essentially? So you basically, when you say quantization, we basically start with the classical system, right? And then we look at the classical phase space, and then we replace the classical phase space by the abstract vector space. Right? So all this xp, they are replaced by the corresponding operators, right? X hat, p hat, and so on. And in the same way, we replace h by the h hat. Now, the interesting thing here is, okay, I'll get there in a second, but let me write down first the quantization rules then. So what we do is we have a bunch of operators and we impose some commutation relation for them, right? So that's what quantization would mean. So we're going to impose this following commutation relation because now they're all operators. Pj, so I delta ij, right? So this is the usual. And then as I earlier mentioned that these two are conjugate. So I, and also the alpha n, alpha mj, they're gonna also have the corresponding Tootle version. And then this is gonna be n delta ij delta m plus n 0, something like that. And also finally, we have the other one, as I said, the p minus is sort of like the Hamiltonian. So it's like the commutation relation between time and Hamiltonian, right? So that's minus sign. So this is the, now, so you see, you can think of this as, so when you did the mode expansion, we basically transform the problem to like an infinite number of harmonic oscillators, right? So you can think of this thing as a collection of harmonic oscillators, right? So each mode corresponds to a particular harmonic oscillator. And therefore, the problem of quantization essentially is sort of quantum mechanical kind of quantization, right? This Lycan quantization will essentially be very similar to the quantization we do in quantum mechanics. And the other point here is these guys are basically, these alphas are basically secretly, they're basically creation and annihilation operators, right? And that we use in quantum mechanics. Just to give you a sense why is that. So remember that the creation annihilation operators in quantum mechanics satisfy this, right? But here, if I look at this guy, so you can see that alpha n, I alpha minus n I is gonna give us something like n, right? Because this is gonna be 1. Therefore, I can make an identification like an is alpha n over this, and a dagger is basically alpha minus n over some square root, and then they match, because again, you can think of these modes as a harmonic oscillator, so it's not a surprise that this identification can be done. So these transverse modes are basically creation annihilation operators. Okay, now we need a vacuum, right? And then we're gonna create particles from the vacuum, or excited states from the vacuum. So what is the vacuum here? So of course, the vacuum would be something like this, right? We have a 0. We apply this. This is the annihilation operator, as I highlighted in the previous slide, and then you get 0. That's our vacuum. But remember that we are in the Walsh-Sheet description, right? And this is not a true space-time vacuum. So it's sort of the vacuum of a single string. So you can think of this as a vacuum without the excitations being considered, right? So still, and if I see it from the momentum perspective, from the momentum space, that means it has a momentum. So the vacuum we have is basically has another quantum number, right? And it's basically an eigenstate of the momentum operator. So this is our string vacuum. This is our vacuum. This is not the space-time vacuum. This is the string vacuum, right? So basically it's a vacuum without the excitations being considered. So that's our vacuum. Okay, good. So we have now all the ingredients. So we're missing one thing here. So let's go into that. So when we have this constant equations, right? And then we have the the whole thing that I wrote, alpha prime, this alpha prime, p minus over 2, and then this 2p plus, and then this all these expressions, right? There is this 1/2 alpha prime pi, and then there is these modes, right? And then we from here we got this level matching. this m square over 4 alpha prime, I equals 1 d minus 2, and then this is alpha minus I, alpha and I, and then the corresponding twiddle part, right? Exactly the same looking twiddles. So exactly the same expression, except now there are twiddles there. So you see now they're operators, right? These alphas are basically operators, because when you quantize it, we promote it to an operator. So when we promote it to an operator, it's not necessarily they're going to commute, right? So there is a question. Sorry.
Question that
Yeah.
what is the ground state of this?
Yeah, so the ground state again is it's not the space-time vacuum, like it's not a true vacuum, right? It's basically, so when if you look at the mode expansion, there are a bunch of x plus and then the p plus, and then there's oscillations. So if you turn off the oscillations, it's like a guitar string without vibrating, but the guitar string has its own momentum, right? If you like move the guitar, for example, right? But it's not exciting. There's no oscillations. Okay, and that's our vacuum. Is it clear?
Yeah. Just
okay, cool.
like if it is not fluctuating, right? So
yeah, there is no oscillation. Yeah, there is no fluctuations. Yeah. So we are turning up all the
then it's kind of placed longitudinally.
So all the transverse oscillations are gone, right? Yeah. So it has a momentum. It's a string in the space, right?
But like if it is placed longitudinally, then what I know is that like longitudinal waves are not permitted in a string theory. So how do we get the momentum there?
So think of a guitar, right? For example, right? Or like a string or a loop, right? So they are not oscillating, but it's floating in the space, right? So it has a momentum, but it's not vibrating itself, right? The string is not vibrating, but it's actually, but you know, if there's an object, right? It's a string, it will have its own momentum, the center of mass momentum.
Yeah, that is true. But the string as a whole is moving, right? That's what
exactly. Yeah, it's a center of mass momentum. Yeah, you can think of like a center of mass momentum.
Okay.
Okay, good. Sorry, we're rushing time. So one of the thing here is there is a ordering ambiguity, right? Because in quantum mechanics, since they're operators, they're not necessarily commuting. So we do what we call the normal ordering, just to keep track of, just to avoid this ambiguity. So the idea is we put all the creation operators, all the creation operators, we want to appear to the left of the annihilation operator, right? So we do it in a systematic way. And that's what we call the normal ordering. The problem there is if we use the normal ordering here, then it's going to introduce a normal ordering constant. So what that means is the actual expression for m squared is going to be something like this. And then I have to add a normal ordering constant here, something like that. And similarly, the same expression I write for the twiddle one. Right? It's the same expression for the twiddle one. There'll be a normal ordering constant. Now the question is, how do I figure out this normal ordering constant? Right? What is this normal ordering constant in this case? So here I'm gonna be very sketchy, very heuristic. Like it's gonna be a very heuristic kind of argument because it's it's not easy to explain it very quickly. So how do I see it? So let's say the approach is the following. So we're trying to evaluate again the normal ordering constant, and let's consider that we're not really aware of this ordering ambiguity, right? Let's say we're starting with the position that we're not aware of the ordering ambiguity. Instead, we take the naive classical result and directly put it over to the quantum theory. So what do we have? So we have this alpha, this term, right? So alpha minus ni, alpha ni, and then n not equals 0. This was our original term. Now I'm gonna, as I said, we don't really know, right? We don't know the we're not aware of the ordering ambiguity. So you're gonna just write in this, break it down into I alpha ni, and then 1/2 n greater than 0 alpha ni alpha ni. And as you know that this sign of n is essentially telling you which one is creation and which one is annihilation operator. Now let's say put it in the normal ordered form. So if we put it in the normal ordered form now, so it's gonna get 1/2 n less than 0 alpha ni alpha minus ni, and I need the adjustment, right? So for example, if I do a dagger versus a dagger a, if I transform it, then if I write a dagger a into a dagger, then I get a factor, right? I get a 1 from it. So the same thing here. So I get this many extra terms I need to get, and then I have the other part, sum alpha n I and n greater than 0, right? Something like that. Now notice that now I can combine them. So what I have is I get alpha n alpha minus n I n greater than 0. Now this space is going to give me d minus 2 over 2 sum. Right? So it's a problem, right? As you can immediately see that this is a divergent quantity. Right? This is a divergent quantity. So how do you deal with this? Now, so if you think about it, so the physical interpretation of this is it's actually the sum of the 0-point energies in an infinite number of harmonic oscillator. Right? So if you have an infinite number of harmonic oscillator, the 0-point energy is not 0, right? So you get all these 0-point energies accumulated together. So what we do now, so we're gonna, even though it's a divergent quantity, we can still get some interesting physics out of it. And we actually see similar kind of effect when you talk about the Casimir energy, the Casimir force between these two metal plates, right? I'm not going into that. I'm just going to use the prescription. So what is the upshot there is we try to from this abstract mathematical expression, we're going to put it into the sort of like in the physical context. And when you do that, we can introduce a cutoff, UV cutoff, which in this case, let's say something very, very small. So what I'm going to do, I'm trying this mathematical problem into physical situation, fitting it into physical situation. So this quantity, I'm writing it as something like n e to the power epsilon n. And as you can see, you know, for very, very small epsilon, this works, right? The second term vanishes, you get exactly what you have. So this can be written as the variation with respect to epsilon, something like this. And then I can write it down as minus d epsilon, 1 minus e epsilon minus 1. And I can do as expansion. And after simplifying, what I get is something like this. Some higher order expansion. Okay, good. But still, it's a problem because as you can see, since epsilon is very small, this is again a divergent quantity. But interesting feature here is you get something finite here. So the idea is the following then. So our expectation would be we'll have some ways in our theory where we can actually renormalize this problem. So there is a way to get rid of this infinity here by some renormalization scheme. And after renormalization, we're going to end up with something like minus 1 over 12. Okay, but this is okay. So this is a bit strange, right? So maybe I can just rephrase it from an intuitive perspective. So imagine that the strings are an infinite collection of harmonic oscillators, right? So that's sort of we're doing, right, when we do the mode expansion. Now, each of these harmonic oscillators is contributing a 0-point energy. Now, the normal ordering process is sort of like resetting the zero of the energy scale by removing this infinite vacuum energy. So we are basically sort of resetting it. So you can see this normal ordering is sort of as a resetting process. But however, since the operators are non-commuting in principle, so this reordering of the operators introduces a finite shift, and which is basically captured by this -1/12 here. That's sort of like an intuitive way to say that. Okay, but this is, there are other ways to say it. I'm not going into that. Like there is also the beta function, the Ramanujan beta function technique, but there are other ways to reconfirm this. We don't have the time for now. So the point is, after using renormalization, we can write down m square as 4 alpha prime n minus d by d minus 2 24, and also for the level matching, so there is a two-dual version, d minus 2 over 24, something like this, right? Once you plug this number. Okay, good. Now we're going to talk about the string spectrum, right? Let's just start with the ground states. So again, when I talk about the ground state, there is no excitation, right? So this term is gone. There's no excitation for the ground state of the strings. So you can see we immediately hit a problem because we get a minus, right? So m squared is minus 1 over alpha prime. So basically we get m squared is minus 1 over alpha prime, d minus 2 over 6. It's a negative quantity. So, and this kind of particle, so the particles we generate here is what you call a tachyon. It has a negative mass squared. But the way we're going to think about it is the following. So it's sort of the QFT language. So in the QFT language, the way we treat this kind of problem, is so let's consider in a quantum field theory version. So let's say I have a field, right? And then there's a potential. So in the QFT version, when the quantum that when you quantize it, the particle mass is something like this, right? You take the derivative with respect to the field and then set the field to 0. Now, what that means now, this minus in the mass term, is essentially means that if I look at the potential versus the field, we are basically somewhere here. Right? We are at the maximum. So it's sort of an unstable position. Right? So we can think of this as we are expanding around the maximum. And you'll see similar kind of situation when you deal with the Higgs particle in the Standard Model, right? In that sense, it's also a tachyon, the Higgs particle, right? It sort of sits on an unstable minimum, unstable maximum. But the problem here is, string theory is still, we also have the same problem. And then the natural question then would be, is there like a true minimum somewhere else? We don't know, right? We don't know. But the way actually string theory tackles this problem more efficiently is when you think about, so we are doing so far is the bosonic string theory, right? Now, when you add fermions, we get what you call the superstring theories, right? So, and when you add fermions, you get to superstring theory. There are some techniques to get rid of the stacking. So I don't know if Tibor is going to cover that, but there are some ways to do that. At least bosonic string theory, we don't. So, okay. So I'm going to stop there. Now, what about the first so the ground state is a tachyon, right? So what about the first excited states? So to what are the first excited states, I'm going to use the level matching idea. So remember that we had this in the level matching, we had the idea there's a left and there's a right side. Now, the state we have is this guy, right? Now, how do I create the excited states? I'm going to heat that with creation operators, right? So if I heat this with, let's say, a creation operator like alpha minus 1 I, let's say. Oh, so when I'm the vacuum, then I have just the vacuum energy, right, on both sides, and the level matches, right? They're equal. So when I want to create the first excited particles, and let's say I heat it with this, the untwiddle one, untwiddle creation operator, then what's going to do is going to change the right-hand side, right? It's going to create a particle on the right-hand side. But then again, they don't match. Okay, let's try the other one, of course, the twiddle one. Now, of course, if I do the twiddle one, then the problem is now I'm going to get 1 minus A, but here I'm going to have a minus A. So again, there'll be a mismatch. So to make sure that we have the level matching, the reasonable first excited state is basically when I act on both types. So when I act both types, I get this kind of levels. The mass square is going to be something like this. So now I have a matching. So the first excited states are basically these states. Okay. Okay. Now the last point, which is a bit. I need a few more. Can I go maybe 5-10 minutes?
Okay. Yes, please.
Okay, cool. Because it's not the right place to stop. So now, so if you look at this, we have this these guys, right? This sorry, not twiddle, right? We have this these guys. Now, the question is, so the first excited stage that we're creating, and this is good. This is the only natural one that satisfies the level matching. Are they massive or massless? So now, if you think about these generators, right? This alpha I and alpha twiddles. These are basically they transform as a vector under the SO d minus 2, right? Because that's the transverse one, right? So it's d minus 2 representation. And this is basically a subset of the full Lorentz group, right? Which is SO 1, comma d minus 1, right? So it's a subset of SO 1, comma d minus 1. Now, notice that if we, so the way I'm going to approach this, I'm going to consider first it's massive, and then I'm going to consider what happens when it's massless. So if I consider first these states are massive, then it's going to form a representation of SO d minus 1. Well, how do I see that? So for example, I can look into the rest frame of the mass particles, and the momentum, I can write it as like P, 0, 0, 0, 0, 0, right? Something like that. So you can see I have basically a SO d minus 1 representation. This is sort of the little group, you can call it. Now, the problem here is this structure is telling us there are d minus 2 square possibility, right? The square number of states are there. So the point here is there is no way we can package that many states in this group.
Shajid, we can't hear you.